So now let's look at L'Hopital's rule and how we can use it on some indeterminate forms of functions. As a quick review, recall that for L'Hopital's rule, if I have some limit of a rational function f of x over g of x, if the numerator and denominator both approach 0, or if the numerator and denominator both approach some form of infinity, either positive infinity or negative infinity. I'll write that as sort of plus or minus infinity. Then we can oftentimes get the limit by saying that the limit of the original rational function is going to equal the limit of the rational function with the derivatives of the numerator and denominator. And I showed this in a previous video. But now we're going to look at what happens with some indeterminate forms. So this is great if I already have a fraction, but what if I don't have a fraction? And so there are these cases where I can have, and I'm going to just write this notation here, but I'm really talking about functions that are approaching 0 and approaching infinity. I'm not actually going to do 0 times infinity. I have a function approaching 0 and a function approaching infinity. Or what if I have a difference of functions where both functions are approaching infinity? And then finally I have some exponential or power functions where either I get one of these forms. I get infinity to the 0, 0 to the 0, or 1 to the infinity power. And all of these are indeterminate. I'll talk about why we aren't sure if these functions work out, what they're going to get to unless we look more deeply. But I can use L'Hopital's rule, and I'll be specific on each, but the idea is I want to rewrite each of these as a rational function, a function as a ratio of two other functions, and then do the L'Hopital's rule from before. The first indeterminate form we're going to consider is 0 times infinity. And so it's indeterminate because we know that 0 times any real number n equals 0. And we know that n times infinity for any n greater than 0, not equal to 0, will equal infinity. So you have these two cases. One of these is trying to collapse everything to 0. The other one's trying to blow everything up to infinity. And the question is, as these functions are approaching both of these, which one wins? This can be anywhere from actually negative infinity all the way up to positive infinity and dne. So the most common way to do this is first rewrite as a fraction. And when I rewrite as a fraction, I'm going to end up either rewriting this as a 0 over 0 case or an infinity over infinity case, and then evaluate using L'Hopital's rule. And it's actually pretty easy once you get the trick to rewriting as a fraction. I'll show an example, you'll see the trick, and a lot of these work the same way. So here's our first example. I want to evaluate this limit, and I see that in this case, x is approaching infinity. That means 1 divided by x is approaching 0, and the sign of 0 is 0, so this term is approaching 0, and we have this infinity times 0 case. Unfortunately, I don't have this as a whole fraction, but I can easily rewrite this as the limit, as x approaches infinity, of, I'll leave the sign in the numerator, so sine of 1 over x, and I'll divide by 1 over x. So let me put a little aside here, because let's just say 1 divided by 1 over x is the same thing as 1 times x over 1. Dividing by a fraction is the same as multiplying by its reciprocal, which is just x. So I basically took this term and got it down into the denominator of the denominator. Now, when I look at this, the numerator is approaching 0. The denominator is also approaching 0. I can use L'Hopital's rule and rewrite this as the limit as x approaches infinity. I take the derivative of the numerator. The derivative of sine is cosine. So I have cosine of 1 over x. The derivative of 1 over x is negative x to the negative second. I put a little because here. So the derivative with respect to x of 1 over x is equal to the derivative with respect to x of x to the negative first, which is, I bring the negative 1 to the front and subtract 1 from the exponent. I look down here, I just have the derivative of 1 over x, so that is same thing here, negative x to the negative second, and the x to the negative seconds cancel, the negatives cancel. As x approaches infinity, 1 over x approaches 0. The cosine of 0 is 1, so this limit is equal to 1. The next indeterminate case. So in this case I have sort of an infinity minus infinity, and infinity doesn't work the same way as real numbers. Usually you would think something minus itself is going to be 0, but infinities can be much larger than each other. Just as a brief example, I may get into this more later. There are other videos up about this, but if this infinity is measuring the number of irrational numbers, and this infinity is the number of rational numbers, this will still be an uncountably infinite number when I subtract. Whereas if somehow these are the exact same infinity, which is a very sketchy way to look at things, basically long and short of it is this can be anywhere between negative infinity and positive infinity, and any of the real numbers between. It depends on how we get there. But the idea is actually pretty easy. So all I'm going to do for most of these cases is I'll end up trying to get a common denominator. Then I will rewrite as a single fraction, and once it's in that single fraction, it's going to be in that either infinity over infinity or 0 over 0 case, and then I will use L'Hopital's rule. To evaluate. So here's a quick example of that. When I look at this, as x approaches 1, this actually approaches, the limit of this itself is dne, but it approaches some infinities. Same thing here. Natural log approaches 0 from the left and the right. So this actually does not have a limit itself, but it approaches infinities. From one side it approaches positive infinity, from the other side it approaches negative infinity. I guess I had that backwards. Negative infinity from the left, positive infinity from the right. Same thing here. So what I can do is get a common denominator. So this will equal the limit as x approaches 1 of, the common denominator is natural log of x times x minus 1. So I'll multiply this by natural log of x. So I have x natural log of x divided by x minus 1 natural log of x. And I'll multiply this by x minus 1 divided by x minus 1. So I get x minus 1 over natural log of x times x minus 1. And I'm going to actually distribute through. I think it's a little bit easier to work with that way. You don't have to if you don't want to. And get this in terms of one fraction. So I have the limit as x approaches 1 of x natural log of x minus x plus 1 divided by x natural log of x minus natural log of x. And now I notice when I put 1 in here, natural log of 1 is 0, so I have 0 minus 1 plus 1, that approaches 0. 1 times 0 is 0, minus 0 is 0, so I get that approaching 0 over 0, and I'm going to work over here so I have some room. So I take the derivatives, and I get the limit as x approaches 1. I need to do product rule for this. So I have u, I have v, and the product rule says that I get v times the derivative of u, so that's going to be natural log of x times 1, plus u times the derivative of v, which would be x times 1 over x, which is just 1. I'll take the derivative of this, which is minus 1, take the derivative of that, which is plus 0. I'm not even going to write it. We just did the derivative of x natural log of x. That's natural log of x plus 1. And the derivative of natural log of x is 1 over x, so I have minus 1 over x. Before I even go further, and this is something that I try to stress, I like cleaning up any fractions. Do the algebra, because sometimes you can kick out of these the L'Hopital's rule early if you clean up things like this. So plus 1 minus 1 cancels. And to get rid of the 1 over x here, I'm going to multiply by x over x to get rid of the x in the denominator of the denominator. And so I rewrite this as the limit as x approaches 1 of x natural log of x divided by x natural log of x plus x minus 1. And we consider what happens when x approaches 1. So 1 times 0 is 0. 1 times 0 is 0. Plus 1 minus 1 is still 0. And I can do L'Hopital's rule again, taking the derivative of this numerator and this denominator. And I get the limit as x approaches 1 of the derivative of x natural log of x is natural log of x plus 1. We already did that. Natural log of x plus 1 divided by derivative of x natural log of x is natural log of x plus 1. The derivative of x is 1. The derivative of negative 1 is 0. And finally, when I put in 1 here, natural log of 1 is 0, plus 1 is 1. Natural log of 1 is 0, plus 1 is 1, plus 1 is 2. And this limit approaches 1/2. Final indeterminate case, which is usually pretty easy. When I have one of these forms, usually 1 to any power, and let's just say n is greater than 0, but a real number, this will always equal 1. However, if I have, let's consider b greater than 1, any number greater than 1 to the infinite power, something approaching infinity, is going to explode out to infinity, unless this is sort of going towards 1, or very specifically. We know that n to the 0 power, any non-zero number, is going to be 1. And we know that 0 to any n power is going to be 0. So we say, okay, which one takes over here? Or if I have an infinite number to any positive power, that's going to be infinite. So things are kind of sketchy here, where n to the 0 power is 1. Which one takes over? Does the base of 1 or the exponent of infinity make a bigger difference? Does the base of 0 or the exponent of 0 make a bigger difference? Does the base of infinity or the exponent of 0 make a bigger difference? And here's the idea. We're going to consider this as a function f to a function g. We will rewrite this as the limit, as x approaches c, of e to the g of x times natural log of f of x. Because e to the natural log of f of x is just f of x, and so I get this same base. I guess I'll show that a little bit better. So because f of x to the g of x is going to equal e to the natural log of f of x all to the g of x, because e to the natural log, these are inverses, and this is a power of a power, so I can rewrite it as e to the, multiplying these, g of x times natural log of f of x, and we get here. And then I'm just going to consider what happens up here. So do the limit of the exponent. And the last part, which is just a little trick, make sure you get back to your answer. This is going to give you the exponent's value, or the exponent's limit, but the answer was now a power of e. So let's see an example here. And I see this case where as n approaches infinity, 2 over n approaches 0, 1 minus 0 is 1, so the base approaches 0. But the exponent, not 0, 1 minus 0 is 1. And the exponent approaches infinity, so we're in this indeterminate case. So I start off by rewriting this as the limit, as n approaches infinity, of e to the n natural log of 1 minus 2 over n. And now I just consider this part. So I'll find the limit as n approaches infinity of n natural log of 1 minus 2 over n. This approaches infinity. 2 over n approaches 0, so this input to natural log approaches 1. Natural log of 1 is 0. And I'm back to this infinity times 0 case like our first example. And I'll rewrite that as a fraction. So limit as n approaches infinity of the natural log of 1 minus 2 over n, all divided by 1 over n. And I can see the numerator approaches 0. The denominator approaches 0, and I'll do L'Hopital's rule. So we have the limit as n approaches infinity. The limit of the natural log is 1 over that function. The derivative of natural log. The derivative of 1 minus 2 over n is 0 times, and that's going to be a positive 2 n to the negative second. I'll write it over here, but I'm going to have to erase the reason why to get space to do this stuff, because the derivative with respect to n of negative 2 over n is equal to the derivative with respect to n of negative 2 n to the negative first. I bring the negative 1 out to the front and get a positive 2, and I subtract 1 here. In the denominator, the derivative of 1 over n is just negative n to the negative second. Let me see if I have enough space without erasing this little because. So in here, the n to the negative second cancels out, but the 2 does not, the negative sign does not. So I'll just bring it together. I will simplify some algebra here, and I'm now at the limit as n approaches infinity of, I have a negative 2 over 1 minus 2 over n. Okay, so I just brought the 2 to the numerator here, multiplied by negative. As n approaches infinity, the numerator, of course, still approaches negative 2. It's a constant. This approaches 0 as we're dividing a constant by a larger and larger number. So this 1 minus 0 approaches 1, and this limits negative 2. But we need to remember, this negative 2 was the exponent. So the whole limit, let me write that out, as n approaches infinity of 1 minus 2 over n to the n power doesn't equal negative 2, it equals e to the negative second, or 1 over e squared. I don't really care which way. Usually I don't like negative exponents, but I don't mind which one we have here. Okay, I hope that helped out. Feel free to comment below with any questions.